Okay, you should have already watched the video. It was I can't remember her name. It was a lady doing some excellent lectures on Kepler's laws. I believe she's an astronomer. And essentially, when you're looking at Kepler's third law, which is the most useful, there's 3 laws of Kepler, and it's a really interesting history if you want to read about Kepler. But anyway, the third law is highly useful. Like it'll tell you, you can use Kepler's third law to calculate at what radial distance from the Earth you need to put a satellite so that it'll orbit, say, once a day or twice a day, and that's important for communication satellites. And not only that, it's the law of our solar system. Okay, so let's have a look at that. So, and another thing about college physics is you notice there's an ambiguity. The first law of Kepler said that the orbits were elliptical, but the eccentricity of those orbits for all the planets is nearly zero. In other words, the orbits of all the planets about the sun are nearly circular. They are elliptical, but they're very, very close to circular orbits. So what we do is we approximate the orbit as circular, and that allows us to easily solve this equation where we see that the centripetal force of the circular orbit is exactly supplied by Newton's inverse square law of gravity. And basically, here's what you come up with. I'm not going to repeat that derivation. She does it for you, but right there, that the period squared is equal to 4 pi squared over g mass of the central body. In our case of the solar system, that would be the mass of the sun, right? M, see how that looks like a central body with something orbiting it, that little subscript on that big M? And then you have to multiply that fraction by r cubed. So that, once again, that comes from understanding that the centripetal force is supplied by the gravitational force, Newton's gravitational force. So we get this relationship between the period and the radius of the orbit. Now note that as the radii get bigger, like Mercury's the closest planet to the sun, its period would be the least. So Mercury's moving quickly. It goes around the sun quickly. And as you move further out, like say Uranus, way out there, it's got a huge radius, and its period would be longer, so it's moving slower. So the farther you are from the sun, the slower you're moving. So basically, all the planets have their own year. The Earth year is, how long it takes for the Earth to go about the sun one time. But Mercury and Venus have shorter year. Their year is shorter than the Earth, and say Mars and the rest of the planets have years that are longer than the Earth's year. Now, one more thing that's very interesting is since the mass of the sun in our solar system is so much bigger than the planets, we can ignore the real law. The real law really should be written like this. So I can go in here and do this. And it should be written like this, where we should technically add to this term here the mass of the planet that's orbiting. And actually, there would be corrections if anything is in your nearby neighborhood that has gravitational attraction on you. But anyway, that would pretty much do the job. But however, since the mass of the sun is so huge, we can ignore that term. Now, most of the stars in our universe are actually called binary systems. They are 2 stars orbiting one another. So in that case, you would have to do something like this. Those 2 stars would obey a Keplerian orbit like this. Well, we would need to label one of these as mass 1 and mass 2. So like, we have most of the stars in the universe actually are binary stars. They're 2 stars that orbit one another. And in fact, we can conclude from laws like this that there are objects orbiting black holes because we can't see anything there, but some object is just behaving in this manner with this law. And you can calculate what the central mass would be to cause something to go around like a neutron star or something that's burned out to go around in a circle at a really tight radius really quickly, and it would have to be a black hole. And that's a kind of interesting. And there are actually orbiting, and this is really weird, there are actually things that are like 2 black holes that orbit one another, and they spiral in and merge, and it's such a huge cataclysmic event that it creates gravitational waves that travel through the universe, and those are what these huge interferometers that were just built like 5 years ago on Earth, one in Washington State and one in Louisiana, They can measure ripples in space-time as small as to about 10 to the minus 18 of a meter. That's smaller than a proton. They can actually detect ripples in the fabric of space-time that small, and those are gravitational waves that Einstein predicted some time ago. He didn't even believe they existed. They just were a result of his theory. That's really strange. Anyway, so enough about all that. So let's go back and look at Kepler's third law. Okay, now, so generally it's just algebra. When you're using this form here, think about it. Okay, so this equation relates the mass of the central object, the period of the orbit, and the radius of the orbit. Now notice that if we're given, okay, let's look at this. If you're given the central mass and the orbital radius, you can solve for the period. That's just a straight plug-in to here, and what we do is we just need to take the square root of each side, and then we get the period, right? So you multiply all this junk together and take the square root of it, or raise it to the 1/2 power. That's the same thing. Now, what if you're given the central mass and the period? So you see that we have to have, there's 3 variables. We have to have 2 of them. Okay, so if you're given the central mass of the orbit, which I need to change that. I've changed that stands for Earth. I really need to I like to use this notation here for central body. There you go. Okay, now, so if to solve for R, how do you solve for R here? You take the denominator and you multiply it on this side, and you take the numerator and divide each side by that, and you get that. So it's like you take this and flip it and move it over there, right? You can just flip that fraction and move it to the other side, and then take it to the 1/3 power, and that's what you get, because we're solving for R. R is cubed, so we need to take each side to the 1/3 power. So that would be the equation you would need to solve. So once again, you're given the mass and the period, you get that. Let me change that one too while I'm fixing this document. I wrote this some time ago. I hadn't looked at it in a while. I didn't know I had it. All right, now, what if you're given the period and the radius? Well, then you could solve for the central mass. Because like I say, you need 2 of the 3 variables. You solve for the one you don't know. Now, obviously, if you're given a homework problem and you're only given 1 variable or none, you might have to look up you might have to indeed look up your from an astronomical table what the mass is, or the radii of the orbit are, or something. You can always look them up, and that's a good way to check answers too. Now, okay, so that's Kepler's laws in a nutshell. So we see that we have these ways of doing algebra, and just basically it boils down to using your calculator, because the aggravation of calculating, it just involves these huge masses and huge radii, so you got to watch out. And maybe I should do a video on how to use your calculator and use the exponential function to calculate with it. It's far easier, and avoiding parentheses and things like that, orders of operations with a calculator. I probably should do a video on that. Okay, now, one more interesting tidbit. Let's discuss something called a geosynchronous orbit. A geosynchronous orbit. Okay, on Earth, that would imply that we had a satellite above the Earth that went around the Earth once a day. Once a day. Now, see how it synchronizes with a fixed location on the Earth. Now, let's say we're here in North Carolina. In one day, we go in a circle and come back to where we started, right? So a satellite would have to stay above our position all day long. In other words, we could communicate with that satellite constantly because it's right above us. And so the earliest forms of communication satellites were called geosynchronous satellites. They stayed above a fixed location on the Earth, so there was constant communication between the satellite and Earth. Back then, radio waves. Now we use microwaves like Wi-Fi. Your smartphone frequencies, in the microwave frequencies, like in the gigahertz, to do a lot of communications, and radio with satellites. Now, but the GPS systems, and you've got an extra credit problem on this. GPS systems, they typically need 3 satellites. Why? Well, if you want to locate, like if you're using your smartphone to locate your position, you're going to need 3 satellites to use triangulation, because it's like we're on a 2-dimensional surface on the Earth, and then we have altitude also. So you're going to need 3 satellites, X, Y, Z. And those 3 satellites can give you your position. Now, those satellites, nowadays there's a whole bunch of communication satellites. In fact, we are experiencing a problem of what you could call space junk. There's so much junk out orbiting the Earth out in space that's gotten dangerous, like a little paint chip flying around at these huge speeds can hit something like a surveillance camera on a satellite or something and do some serious damage. And those satellites are expensive. But anyway, so GPS orbits, if you think about that, in those orbits, GPS satellites, they go around the Earth twice a day. So you could calculate the period, right? You know how many seconds are in a day. Well, just take half that. How many seconds are in 12 hours? And then you could calculate R and get the radius at which it's at its orbital radius. Now, remember, if you want the altitude, by the way, if you want the altitude, this R right here is from the Earth's center. So you got to be careful if you want altitude, right? So anyway, I'm just giving you some hints how to tackle homework problems with Kepler's third law. Okay, have a great day.